All right, Module 11. Chi-squared tests are what we're going to be doing, and there's 3 different chi-squared tests. 2 of them are going to be very, very similar. We'll learn about those 2 in the next section, but in this section we're going to be doing the goodness of fit test. I love the chi-square test. The chi-square tests are always really going to help you on your final project as well, because they're going to be dealing with 2 in module. In this next section, we'll be dealing with categorical. And it's a lot of fun. Anyway, so section 11.1, compute expected counts, conditional distributions, contributions to the chi-squared statistic. Check all your conditions, and then we're going to perform the chi-square goodness of fit test and to see if it's consistent with a specified distribution of categorical variables, and then examine individual components of the chi-squared statistic as part of a follow-up. Woohoo! Let's get started. Okay. So in the previous module, we discussed inference procedures for comparing the proportion of successes for 2 populations or treatments. Sometimes we want to examine the distribution of a single categorical variable in a population. The chi-square goodness of fit test allows us to determine whether a hypothesis distribution seems valid. So we can decide whether the distribution of a categorical variable differs for 2 or more populations or treatments using a chi-square test for homogeneity. So homogeneous is how similar things are going to be, like basically how close together, how similar they are. In doing so, we will often organize our data into a 2-way table. It is also possible to use the information in a 2-way table to study the relationship between 2 categorical variables. This is going to be the chi-square test for association or independence, which we will get to, like I said. Okay. All right. So let's see if I want to do this or not with you. Yeah, we'll go ahead. Okay, so Mars Incorporated makes milk chocolate candies. It's milk chocolate. I don't know if you guys have ever been to the Hershey's, to that place. They have a little ride. Anyway, they sing that to you. It's the milk chocolate, Hershey's milk chocolate. Okay, so here's what the company's Consumer Affairs Department says about the color distribution of its M&M's milk chocolate candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% of each browns and reds, 14% yellow, 16% greens, 20% oranges, and 24% blues. Let's say you are given a bag of M&M's and you count each color in the bag. Okay? And then everyone in this class records the number of each color in the bag. Now I want you to find how many you should have according to the percentages given. And everyone in class has recorded the expected counts from their totals. Let's say it looks something like this below. Okay. So a one-way table below summarizes the data from my bag of M&M's milk chocolate candies. In general, one-way tables display the distribution of categorical variables for the individuals in a sample. So here I can see that the sample proportion of M&M's would be 9 out of 60, which is 0.15. Since the company claims that 24% of all M&M's milk chocolate candies are blue, we might believe that something fishy is going on because we only got it to be 15%. We could use a one-sample z-test for proportion from Chapter 9 to test the hypothesis, and here is the true population proportion of blue M&M's. And we could do that for all of the remaining colors. However, performing a one-sample z-test for each proportion would be pretty inefficient and would lead to the problem of multiple comparisons. So, more important, performing one sample z-test for each color wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company as this bag does. So it's taking all the colors into consideration at one time. So for that, we're going to need a chi-squared goodness of fit test. Woo! So the null hypothesis in a chi-squared goodness of fit test should state a claim about the distribution of a single categorical variable in the population of interest. Okay, so basically don't forget, like, the null hypothesis is always what's the, like, what, no change, what's the claim, what are they saying. So here are nulls that the company stated color distribution is correct, so no change. The alternative hypothesis is going to be that it, where did I say, a best fit is the categorical value does not have the specified distribution. In our sample, the alternative hypothesis would be the company stated color distribution for M&M's milk chocolate candies is not correct. So we can also write our hypothesis in symbols. So you could put that the null hypothesis is everything that they said. Your alternative would be at least one of those proportions is incorrect. In the HA, we don't have to say all will be incorrect. We just have to say at least one. And if you put all will be incorrect, I'm going to dock you here. Okay, so make sure if you write it with the math symbols instead of the words that you get it correct in your alternative. Okay, and label what each of those P's represent. So the idea of a chi-squared goodness of fit test is this. We compare the observed counts from our sample with the counts that would be expected if the null is true. The more observed counts that differ from the expected counts, the more evidence we have against the null hypothesis. In general, the expected counts can be obtained by multiplying the proportion of the population distribution in each category by the sample size. All right. Assuming that the color distribution stated by Mars is true, 24% of all M&M's milk chocolate candies produced are blue. For random samples of 60 candies, the average number of blues would be about 14.4. This is our expected count. Using this same method, we can find the expected counts for all of the colors. See if you can do that. And then check to see if you got your orange expected count to be 12, green is 9.6, yellow is 8.4, red is 7.8, and brown is 7.8. So here I can see in the colors, we have our expected counts versus our observed counts. Okay, so we have this table going on. It's kind of like two different lists, basically. Okay, and here's just a graph of it. We see some fairly large differences between the observed and expected counts in several color categories. How likely is it that the differences this large or larger would occur just by chance in random samples of size 60 from the population distribution claimed by Mars? To answer this question, we calculate a statistic that measures how far apart the observed and the expected counts are. This is called the chi-square statistic. Okay. Okay, so the definition, the chi-squared statistic is a measure of how far the observed counts are from the expected counts. And this is going to be our formula. Chi-squared, it looks like an X, but it's kind of like a pretty X. I don't know, a curly X, but it's like a bigger X than just a regular little X, and then you put the squared with it, and that's called chi-squared. Don't forget this little guy means to add everything. So you're going to take your observed minus your expected, square it, divide by the expected, and add all of those up. And that's your chi-squared statistic. So we're going to do this by hand, and I'm going to show you how to put it in your calculator. So here on this table, if I wanted to find the chi-squared statistic, I'm going to take my observed minus my expected, square each of those and add them up. So I got my chi-squared statistic to be 10.180, approximately. So think of the chi-squared as a measure of the distance of the observed counts from the expected counts. Large values of chi-squared are stronger evidence against the null because they say that the observed counts are far from what we'd expect from the null if it was true. So small values of chi-squared suggest that the data are consistent with the null hypothesis. Okay? So larger values of chi-squared are stronger evidence against the null because it's saying that they are far from what we would expect. So in your calculator, you can do this. You can go put your data, like we said, into those two lists. Okay, so put your observed into list 1, put your expected into list 2. Then we're going to go onto our test and go stat test and go to the chi-squared goodness of fit test. So whenever you have the two lists going on like this for chi-squared, it's a goodness of fit test. Then for your observed, put list 1, because that's where we put it, and the expected put list 2. Degrees of freedom, you had 1, 2, 3, 4, 5, 6. So you're going to have 6 minus 1, which is 5. And then hit calculate, and you can see your chi-squared statistic. Okay, and you also find your p-value here, which is nice. All right, here are the results of Ginny's 60 rolls of her ceramic die. And we'll get into more. If Ginny's die is supposed to be fair, fill in the expected counts. See if you can do this. All right, so see if you got 10 for each of those. And now calculate the value of the chi-squared statistic. Here, if you wanted me to, so you're going to take your 1/6 times your 60 trials, because the probability of getting a 1 would be 1 out of the 6 sides, so that's going to give you 10. Probability of 2 would be 1 out of the 6 sides, times your sample of 60, which would be 10. And that's going to be the same since they all have the same probability of a fair die. All right, so now calculate the value of the chi-squared statistic. I don't care if you do this in your calculator or by hand. And I got it to be 3.4. All right, so now that we can do that, let's keep learning some more. The sampling distribution of the chi-squared statistic is not a normal distribution. It is a right skew distribution that allows only positive values because chi-squared can never be negative. Think about that. If you are squaring everything here and adding, you can never get negative values. Okay. So when the expected counts are at least 5, so actually it's a little bit more than this. So you want 20% are at least 5 and all are at least 1. That's kind of more, okay. So 20% are at least 5. And all of the expected counts are at least 1, then the sampling distribution of the chi-squared statistic is close to a chi-squared distribution with degrees of freedom. So it's the number of categories minus 1. So here you can see, as your degrees of freedom increase, you're going to become more and more normal. So conditions, again, no expected counts are less than 1 and no more than 20% of the counts are less than 5, and the sample is random, and you have independence. So we computed the chi-squared statistic back with our M&Ms to be 10.108, and now we're going to go find what our p-value would be. Okay. So we're going to go into our table, and we're going to go under the chi-squared table. I think that's table C. We're going to look in the degrees of freedom row to be 5, the 6 minus 1. Okay, and we're going to find our chi-squared statistics. So here it's going to be between the 9.24 and the 11.04 because we had a 10.10 or 10.18. So we know that the chi-squared falls between the critical values of 9.24 and 11.07. Corresponding areas on the right tail of the graph would be between the 0.10 and 0.05. So the p-value is going to be between that 0.05 and 0.1. So this is pretty vague. That's why we like to use the calculator. Okay, since our p-value is between that and it's greater than 0.05, we can fail to reject the null. We don't have sufficient evidence to conclude that the company's claim color distribution is incorrect. And when we put it in our calculator, we got our p to be 0.07029, so we can find it exactly and see that that is greater than the 0.05. Yay! All right, in our calculator, another way that you could find it if you just wanted to find the p-value. I don't do this as often because I think it's pretty easy just to put it all in the data. But if we know our chi-squared value, we could do a chi-squared CDF and do your 10.18 to infinity and your degrees of freedom of 5, and you could get your p-value there. So carrying out the whole test, we gotta put it all together now. Make sure that you check your conditions, random, your expected counts, that you have 20%, at least 5, and all at least 1. Some people do go that all expected counts are at least 5. AP will kind of take either one of those. They won't ever give it to you where it wouldn't meet one or the other. Okay. Independent. So you want to check that it's either with replacement or without replacement. If it's without replacement, you're going to have to check that 10% condition just like before. Okay. So you can set up your null and alternative hypothesis. Remember, if you start with your symbols, then you need to state what all of those are. Otherwise, I think it's easy just to kind of put it into words. Is correct, is not correct. And remember here, at least one is incorrect. Okay. You can find your chi-squared, find your p-value, and then state in context. Wow, that is really horrible. Okay, so before we start using the chi-squared goodness of fit test, we have two important cautions to offer. The chi-squared test statistic compares observed and expected counts. Don't try to perform calculations with the observed and expected proportions in each category. And when checking the large sample size condition, be sure to examine the expected counts, not the observed counts. Okay. A lot of people, when they go check for the large sample size, they'll only look at the observed counts, but you need to always find the expected counts on these and all of the chi-squared stuff. Always find the expected counts. All right. Just more about that null and alternative we've talked about. So let's do an example. Are bursts evenly distributed across the days of the week? The one-way table below shows the distribution of bursts across the days of the week in a random sample of 140 bursts from local records in a large city. Sorry, do these data give significant evidence that local bursts are not equally likely on all days of the week? All right. So, what do you want to do first? You could go find the expected counts. You could write your null and alternative, check your conditions. Let's go ahead and write up our expected counts. So how many days of the week are there? 7. So if I take 1/7 times 140, what do I get out? 20. And that's going to be the same for all of these. So all of the expected counts are going to be 20. Because they all have the same probability of the 1/7. All right, so let's state our null and alternative hypothesis. They are evenly distributed. They are not evenly distributed. Or you could put it with the symbols. Again, at least one is not 1/7 is what you would need to write here. Or you could say one of these is incorrect. If the conditions are met, then we can do the chi-square goodness of fit test. So let's check our conditions. Random, the data came from a random sample, told us. Large, we found all of the expected counts to be 20, so we're good there. Independent individual bursts in the random sample should occur independently. Since we are sampling without replacement, you can't put a baby back in. That sounds horrible. Okay, so you're going to check your 10% condition. Okay, and so take your 10 times your sample of the 140, and you can say that there are at least 1,400 bursts in that large city. Okay, so it should be the case in the large city. All right, so now state what test you're going to use. You could have stated that before as well. So we're going to perform a chi-squared goodness of fit test. So when we have the two lists, we're going to do a goodness of fit test. And you can put this in your calculator, or you can do it all out by hand. Sometimes it's just fun to do it by hand. I don't know why, but okay. So I got my chi-squared statistic to be about 7.6. And again, you can put that in your calculator, and it gives you 7.6. And if you put all that in your calculator to those two lists, I got a p-value of 0.26889-ish, rounded off. Okay, so you could go look in the table and see what it's between, and you're going to see that it's going to correspond to 0.225 or greater here. So we know that our p is greater than 0.25. Okay, you could find the exact technology with your calculator, okay, either by putting it all in the chi-squared goodness of fit test or by using this chi-squared CDF. But making our conclusion, whichever way you do it, because the p-value is greater than 0.05, we fail to reject the null hypothesis. So these 100 bursts don't provide enough evidence that this is not statistically significant to say that all local bursts in this area are not evenly distributed across the days of the week. So again, if you wanted to put it in your calculator, you could also draw it there too as well. Okay, so you could see the graph there, definitely skewed right. All right. So let's see how you do on this one, inherited traits. So here's the whole question. And see if you can find all your expected, find your chi-squared, set up your null and alternative, check your conditions, all that fun stuff, make your conclusion in context of the problem. And check your answers. Make sure you are finding all of those expected counts. Okay, so show all that work somewhere. State what test you're using. Find your chi-squared statistic. Find your p-value. In this case, since it's smaller than 0.05, this is statistically significant. So we have convincing evidence that the biologists' hypothesized distribution for the color of tobacco plant offspring is incorrect. Okay, so just a little follow-up. And here are your summary for the chi-squared goodness of fit test. And we're going to do the association and independence here in the next section. Okay, and we'll start that in next time. Whenever you get to it. Maybe it's right now. I don't know.